Hello, 11th graders. So we are wrapping up our 6-6 notes today. So as we tend to do with a lot of these notes, the very beginning part of this lesson is that we're learning about the mathematics behind what we're learning. And then we move on to the end of each lesson talking about, well, why do we care about this and how is it being used? And since we're in an IB applications course, all of your IB questions are going to be revolved around something to do with why do we care about this? And you're going to be given word problems that apply this mathematics into all the different ways that they're used in the real world, which there are so many with Voronoi. So I've got a couple pictures here on your notes, which are just a small sampling of the examples of Voronoi diagrams and their uses. If we're talking about areas of which that we are calculating that you have one thing that whole area is closest to that one thing, you can talk about that with a lot of things. If you're talking about restaurants, if you're talking about stores, if you're talking about hospitals, if you're talking about disease vectors and populations of epidemics spreading out, and you're talking about an area where like this is the closest person to them that's been infected, and what happens when that area gets smaller and smaller versus when that area gets larger and larger, and what are those effects in the real world. I'm sure we can all think about something like that. So things like airports, you can see here on the left-hand side of your notes that you've got a simulation of a globe, and you've got all these tiny and sometimes larger bubbles that have expanded until their edges have met and flattened out. And this is a Voronoi diagram of airports. I don't believe there's actually an image of the world or of the land on that picture. I think that you just get the idea of the shape of the continents based off of those bubbles. Those bubbles are tightly condensed in areas where there's population versus way out in the Pacific where there's nobody for hundreds and thousands of meters. That you tend to get this open space. And so the clustering of those bubbles gives you the effect of this idea of there being landmass there when we don't actually have the true outline of the landmass that's actually there. So kind of cool to see how Voronoi diagrams can paint a picture of a population just by the shape of bubbles. On the right-hand side, we have a map that's actually from the cholera epidemic. I'm not even going to embarrass myself by trying to tell you what year it is. I should know more, but I really highly encourage you actually to go onto YouTube and go down a little YouTube rabbit hole of like cholera epidemic. John Snow, yes, not that John Snow, but a different one, was an epidemiologist. Okay, I guess I'll embarrass myself. I think early 1800s. And he had suspected that he knew what was causing the cholera epidemic, but he didn't have the data to back it up. And so he suspected that it was water sources. And so as a result, he decided to go to government bureaucracy and ask for the information that they had available on the cholera outbreak. And so he got the addresses and the death numbers, the death tolls from the government. And he went and he created, and you can see that's what this map is right here that you see on your notes, are these dots and clusters of deaths from cholera. And so he used those and created what we now call a Voronoi diagram to pinpoint where those clusterings were happening. To rather focus on the sources of water in that area and create a Voronoi diagram to figure out what area is closest to which water source. And so as his water source as the center of each cell, he noticed that the majority of all the deaths were in the same cell, meaning that they were coming from one source of water. And so he decided to test his theory by removing the handle of the water pump that was there, therefore concluding as the deaths lowered that his hypothesis was correct the whole time. Kind of cool. So those are two examples. You can also see a picture of what looks like children's art because it is. So Pixar actually uses Voronoi diagrams as a way to create cool patterns on scales, as well as if they're just looking for a cool pattern to put on something. I think in the video that I saw that explained it, which you can find it too on Khan Academy, I almost attached it to one of your warm-ups for today, and it's geared towards kids. So I didn't want you to think that as 11th graders that I saw you as babies. So I didn't post it, but it's actually kind of really interesting to see how they use Voronoi diagrams to determine patterns. They had it as like the cake pattern on a scene in The Incredibles. So they use it as this like go-to pattern because you can look at that Voronoi diagram that's on the dinosaur arm or leg right there, and you can see where the Voronoi diagram comes from. And as we start to build more and more Voronoi diagrams, you can see these patterns that emerge that could create these interesting, they look random, but they're not actually because they're programmed patterns that come from it. So there's we use these Voronoi diagrams to give us information about spatial awareness and how that plays into the climate of the time or what we're researching, whether it's the cholera epidemic or whether we're determining what part of town should build a new chocolate shop, or if we wanted to figure out what area of town is least represented by a school. So if there's like some places that are really far away, or if there's some schools that are really far away from one specific area, if you built a school in that area, would you then be equally distributing the possibility for education among more people? So there's two different ways that we can look at Voronoi diagrams. And the first one that we're going to talk about is the nearest neighbor interpolation. So remember we talked about interpolation and extrapolation. Remember that interpolation is that when we're looking at data that we've given and we're picking out information within that data, as in like we've got a certain range of data that we're looking at. Here it's a map, so it's a two-dimensional space that we're looking at. Before we talked about like a list of numbers where we said, okay, from years 2001 to 2021, this is the information that we pulled, but it wasn't every single year that we pulled. So we could say, we'll use this data to make an interpolation about what happened in 2000. I don't even remember the original year span that I just gave you, but if we were within the year span, I think like 2011 within the year span that we were given, even though we don't necessarily have information that we pulled or got out from that information or from that sample set, we can then make an interpolation given the range of the data, as opposed to extrapolation, which you'll hear people say like, oh, well, I extrapolated this. It means that we're looking outside of your data set. And at that point, we're making an educated guess. It's much better than just pulling a guess out of thin air, but it's not necessarily true. There are a lot of other things that could happen if we're talking about extrapolation that are outside of the realm of what we studied. So all that to say, nearest neighbor interpolation is that we are looking inside the data set that we've been given, or the information that we've been given, in this case, a map, to then pull information out about that area. The idea is that if you fall within a certain cell, then you follow all of the information that goes with that cell. So for instance, we have a map of Pueblo, Colorado, and this is from your book. That measures rainfall in inches. And we want to estimate the rainfall at a location near one of the rainfall gauges. And we simply use the nearest gauge. So we want to estimate what the rainfall was at point P. So all of those other points that have decimals are rain gauges that are around the area. They've mapped them specifically. And I'm sorry, there's a fly that's being very aggressive. So all of those points that have decimals are rain gauges that have been placed around the area of Pueblo, Colorado, and we want to determine where P lies closest to. Now, there's a lot of information that we don't know about this map, and I'm sure if I took a second to let you guess about it amongst yourselves, what are some things that you don't know about this map? We don't know what those gray lines are. I don't know if it looks like roads and maybe rivers, but maybe just roads. And so maybe that's the rain gauges are at certain buildings that are around the roads, or they've just been placed in a certain area. But we don't know what terrain looks like. We don't know what the elevation looks like. Between two rain gauges, we could be talking about above tree line. So we could be talking about in a place that gets less rain because it's so high up versus a place that's really low. And having the more sites you have and the more cells you have, you can always narrow down the difference between elevation and the difference between climates, the more rain gauges you have. But then at some point, you're just putting hundreds of rain gauges in a very small area, and you might as well just cover the entire world in rain gauges. So you have to do some sort of interpolation of the information you've been given. All of this to say, we need to make a Voronoi diagram to represent all of those rain gauges and the nearest area that they represent. So what we're going to do, because those are a lot of points, and I don't want to I will never make you make a Voronoi diagram by hand based off of this many points, and nobody has time for that because we have technology that is readily available for us. So I'm going to show you how to use technology to make a Voronoi diagram so quick, you're going to be really mad that you're not allowed to use technology for all Voronoi diagrams. So hang on tight, and we're going to scooch on over to a different program.